Hello and welcome back. Today we are talking about sample standard deviation. If you did not watch the video on understanding standard deviation, population standard deviation, or my population and sample variance videos, I recommend going back and giving those a check. Assuming you did, let's carry on. Quick recap: population versus sample. A population contains every observation of interest. A sample is only a subset of the population. Cool. So here we have our formula. It's very similar to our population standard deviation formula, and it's also simply the square root of our sample variance formula. We should notice that. We've gone over this formula a couple times now. Just to recap, S is our sample standard deviation. In previous videos, I was giving this symbol the wrong name. I was calling it epsilon, and I actually looked into it, and it's really sigma. This is a capital Greek letter sigma. Okay. Typically it's referred to as summation notation, summation as taking the sum of. But we like to get things right here. So going forward, I'll call this by the proper name. This is sigma. Anywho, sigma summation notation means the sum of. We're going to get multiple values for this point here, this portion here, and add them all together. X sub I represents each X value of the data. X bar is our sample mean. When working with a sample, we use the symbol X bar. When working with the population, we use the symbol mu. At the end of the day, it doesn't really matter as long as you get the right answers, but it's good to use the proper notation. And N is our sample size. And again, just like sample variance, we do N minus 1 in the denominator. It's the only change we make. Okay. And here, why do we divide by N minus 1? When we calculate the standard deviation from a sample, using N tends to underestimate the true population standard deviation. Dividing by N minus 1 compensates for this and produces a better estimate. This adjustment is called Bessel's correction. Probably not something you need to know. However, it's always good to know where things came from. Bessel's correction is what we call this. Cool. So here we have an example. Here's our data set, 2, 4, 6, 8, 10. Our X sub 1 is 2. Our X sub 2 is 4. Our X sub 3 is 6. Our X sub 4 is 8. Our X sub 5 is 10. And N equals 5 because we have 1, 2, 3, 4, 5 observations in our data set. And highlight over here, the portion of the equation we're focusing on. This is our X sub I. These guys, we're going to have 5 pieces to this. And N right here is going to be 5. Okay. This is just given data. We haven't even started the steps yet. All right, let's start. Step 1, calculate the sample mean, X bar, okay? So we've done this a bunch now. We should know by now. The mean is the sum of all observations. This is a shorthand notation for that, divided by the number of observations. So the sum of our observations is 2 plus 4 plus 6 plus 8 plus 10, divided by 5 observations, equals 30 over 5. Our sample mean X bar is 6. 30 divided by 5 is 6, okay? And that's this part of our equation here. Step 2, find each deviation, which is our X sub i's minus our X bar, okay? So that's each X value we have minus our average. Our first X value, 2 minus average of 6 is negative 4. Second value, 4 minus our average of 6 is negative 2. Third value, 6 minus our average of 6, 0. Fourth value, 8 minus our average of 6 equals 2. And fifth value of 10 minus our average of 6 equals 4. And that's just the inside the parentheses part of our equation here. All right. Step 3, square each deviation. So we take our found values from the previous step and we square them. Negative 4 squared, 16. Negative 2 squared, 4. 0 squared, 0. 2 squared, 4. 4 squared, 16. Quick comment here. I didn't address this in the other videos and I regret not doing it. So I just want to talk about it quickly here. You notice how I write the negative 4 squared, or the negative 2, it doesn't matter, but I write it like this as opposed to this. These both mean 2 different things, and it's very important that we include the negative inside the parentheses. This statement here reads as negative 4 times negative 4. Whereas this statement here reads as something a little bit different. This actually reads as negative 1 times 4 times 4. So this statement right here will give us a positive 16, where this statement right here will give us a negative 16. You might notice on your calculator sometimes where you just plug in this and you get a negative out, and you might be wondering why. This is the reason why. So whenever I deal with negatives raised to exponents, I always put them in parentheses to avoid this confusion here. Okay. Quick side notes. Let's erase all this. All right. Anywho, we square each deviation, we get these values, and now this is this part of the equation here with our square included. Cool. All right. Step 4, add the deviations. So just like before, I'm going to draw lines. This right here, x sub 1 minus x bar squared gives us the 16. X sub 2 minus x bar squared gave us the 4. X sub 3 minus x bar squared gave us the 4. X sub 4 minus x bar squared gave us, oh, sorry, the last one gave us the 0. That one gave us the 4. And then x sub 5 minus x bar squared gave us the 16 here. Nothing crazy here. This is just adding our values we got from this step. Okay. Let's get rid of these. And when we add all of them up, 16 plus 4 is 20. 4 plus 16 is another 20. 20 plus 20 gives us 40. So the summation, the sum of all of our squared deviations is 40. Cool. All right, now we take that and divide it by n minus 1. So here's the summation of our squared deviations divided by n minus 1. We already determined this was 40 from the previous step. N is 5. 5 minus 1 gives us 40 over 4, gives us 10. Okay, and now we just simplify the part that's inside the square root, and we should recognize this is the same exact thing as our sample variance, okay? And we just take our last step and we square the whole thing. The equation, or sorry, we take the square roots, my apologies. Here's our equation, square root of 40 over 4, square root of 10. Our sample standard deviation is approximately 3.16. And we could say the data values are typically about 3.16 units from the mean. And again, we say typically because what this means is any given value on average is 3.16 units away from the average. That's super wordy. So we can say any given value is typically 3.16 units from the mean. They mean the same thing, but we don't want to repeat ourselves. Okay. So just comparing the two, population versus sample standard deviation, using the same data set. So we used the same exact data set for the population standard deviation in the previous video. We got square root of 8, which is about 2.83. For the sample that we just did with the same data set, we got root 10, which is approximately 3.16. We should notice that the sample standard deviation is slightly higher because of the n minus 1 adjustment. Whenever we divide by a smaller number, we get a bigger value output, okay? So the sample standard, whenever you do sample standard deviation or sample variance, it should always be a little bit higher than the population one, but it should be close enough. We're looking for like a close approximation, not exact value when we do these type of things. All right. And here we have a practice problem. Find the sample standard deviation for both these data sets. And we could assume that both of the data sets, this is just a sample of a larger data set, but this is the sample that we're focusing on. First one, we have the set of 5, 5, 5, 5, and the second one, we have the set of 3, 5, 7, 9, 11. All right, feel free to pause here and take a stab. All right, hopefully we paused and looked at this. Let's take a look at the answers. Just like last time, I didn't do work for the first one. It's simply 0. We know it's 0 because each observation is the same number, 5. If we find the average of this, we get 20 over 4, which gives us 5. Our deviations, they're all going to be 5 minus 5, which gives us 0. This whole thing's just going to turn to 0. Again, if you're working on this in class, show your work. I got lazy here. Second one, can't quite do that, so let's take a look. All of our x values listed to the left. X sub 1 is 3, x sub 2 is 5, x sub 3 is 7, x sub 4 is 9, x sub 5 11. We have 5 elements of our set, so n equals 5. We take the average of 3, 5, 7, 9, 11, and we get 7. So our x bar is 7. Our deviation squared, again, each value minus the mean. 3 minus 7 is negative 4. Squared is positive 16. 5 minus 7 is -2, squared is 4. 7 minus 7 is 0, squared is still 0. 9 minus 7 is 2, squared is 4. And 11 minus 7 is 4, squared is 16. Okay? Plug it into the equation. We take them all our values here and we add them up. 16 plus 4 plus 0 plus 4 plus 16. We divide it by n minus 1, which in this case is 5 minus 1. We get the square root of 40 over 4, which is the square root of 10, which is approximately 3.16. Cool. And that's everything I have for you on sample standard deviation. Thank you for tuning in. As always, a link to the notes will be in the video description, and I will see you next time. Take care.